Hi, welcome back. Let's talk about the small signal response in a MOS capacitor. We had just sort of hypothesized how the equivalent circuit model should look like. It's a series capacitance of an oxide capacitance and a semiconducting capacitance. And let's look at the overall frequency response of the system and look at this in the context of a small signal. So here we're doing MOS caps in a small signal response. And to go back into the physical picture, in accumulation, you have the junction capacitance, where you have charge of the voltage that you applied is negative. So you pulled up this Fermi C from the flat band condition. You bend up the bands in the semiconductor, and you let holes come in from the contacts, and the electrons on the left are coming in from the battery by the positive bias, and you have charges that are separated by an oxide. Okay, so there's a junction capacitance in accumulation that is close to the oxide capacitance. Again, oxide capacitance, simple plate capacitor, which is the dielectric constant divided by the distance. So simple plate capacitor, okay? Now, the charge in the semiconductor is not perfectly a sheet charge. It has a spatial distribution. There is some band bending that one ought to account for. And that will lead to some non-ideality in a way that you don't have a charge that is truly a sheet charge. Like at the semiconductor, at a metal surface, you assume it's virtually infinitesimally small. So you will have some, if you represent this distribution of charge that is sitting here, I'm going to sketch it a little bit bigger. So here's the potential. So you will have semi-classically a triangular notch of charge sitting here, and it's pretty clear that this charge is not just a perfect delta function right here at the interface, okay? Obviously, quantum mechanically, you would have even wave functions sitting here that are distributed, right? So two wiggles, etc., multiple states. Clearly, the peak of this wave function would not be exactly at the interface, okay? So it is clear that the charge is not directly sitting on the interface, and you can account for it by separating it, treating it still like a delta function, so to speak, but this delta function is separated from the interface by some effective distance, okay? So, so if you have these charges that are separated like this, and it's a series capacitor where you have different dielectric constants, you can model that with two series capacitors, like what we had done before. And what you do is conceptually, you introduce a virtual charge here on the central node. If you remember your first leaps as electrical engineering courses, you had a series capacitance like this. You can calculate this floating potential here in the middle. And basically the argument is here that the charge, that whatever sits here, is equal and opposite to here on the other plate. So that is what you assume here. You have some positive charge that sits at the semiconductor tail end, and you have some negative charge here that sits at the metal oxide interface. And in between, you have two delta functions that cancel each other, but it allows you to calculate the series capacitance in the system, where now the fields drop off over different dielectric constants. Okay, so we can carry that through, that the overall junction or gate capacitance in this sense here in accumulation is the series capacitance of the oxide capacitance and the semiconductor capacitance in accumulation. And we just define this accumulation semiconductor capacitance just in the same way as what we've done with the oxide capacitance. It just has a different dielectric constants. It has the semiconductor dielectric constant, and here it has the effective width of the accumulation layer. Okay, so 2 series capacitors, and we are working in this branch here in an ideal sense. This WAC shouldn't move a whole lot as a function of bias, but you know that can't be quite right because you do have this band bending here, and the stronger the band bending, you will move this charge slightly. So only in the ideal sense will this be completely flat. But let's go with that for now and assume that WACC is very small and it doesn't vary too much with the gate voltage. And we have 2 capacitors in series. All right, now let's look at the junction capacitance in depletion. Okay, we're reversing the bias on the junction. We are now having a pile of missing electrons. So we have positive charge right in the metal, induced by the positive gate voltage that we applied. There's no current flow. Fermi level is flat. We're bending the bands. We don't bend the bands very heavily, but we're creating a depletion region over here. Okay, so we're now working in this branch here, where the capacitance is expected intuitively to go down because we're separating the charge further, right? So let's figure out some expressions in the system. So the point here is, again, we have some depletion region length and we have some effective charge that we are beginning to wiggle up and down here at the tail end of the depletion region. Okay, we're effectively only looking at differential charges because we're looking at a small signal response. We're not looking at the total charge in the overall system. We're varying charge here at the tail end. Okay, shouldn't write red over red. So, but we have a negative acceptor charge, and we're adding and subtracting some of that charge at the tail end in the semiconductor at a certain distance. Okay, now, this is the blinking thing that's hard to see maybe on the slide here, but we're basically adding charge here at the tail end as a function of a small signal response. Okay, so obviously we made our dielectric separation, our plates, we made them apart, come apart further and further. Okay, so now we're having again an expression for the overall junction capacitance and depletion. Again, it's just a simple series capacitance, and we're plowing through our expressions just like what we had before. But now the W we have is the depletion with W that is entering this expression. Again, we're not integrating overall in this charge anymore. Here we're looking at the differential charge at the semiconductor end for this AC signal. Okay, and we're ending up with these ratios between kappa and X in the semiconductor, and the width of the semiconductor, and the kappa in the oxide, and the oxide thickness, and the kappa in the semiconductor, and the width of the depletion in the semiconductor. All right, so as this depletion region grows, obviously the capacitance will go down. Let's figure out how it goes down. The expression here is a representation of the total potential that is being dropped. So we know one component drops over the oxide, the other component drops over the semiconductor. We have calculated these expressions over and over again in the PN junction, and the BJT, and the HBT. And so these expressions should look familiar to you now. And you can solve this expression here for W, the width of the depletion region, as a function of applied gate voltage now. So you can do that and solve for W, and effectively you write it down for this ratio of W over the oxide thickness and the flipped ratio of the dielectric constant in the oxide and the semiconductor, because that's what shows up in the expression up here, right? Now, The expression is a little bit unwieldy, has some coefficients in it. You can define a V delta in here that ultimately makes your expression that shows up here a little easier. So you have the junction capacitance in depletion is dependent on 1 over the square root of the gate voltage, and that is what you see going down here, okay? The rest are some coefficients that you can lump together. All right, so now let's look at this capacitance in inversion. And we're going to look at the low frequency first. There's 2 components. There's the low and the high frequency one. And let's look at the low frequency one first. Okay. At low frequency, we can generate electrons in the semiconductor here. Minority carriers due to generation through traps. That will minimize the overall energy stored in this capacitor, and therefore, instead of wiggling electron holes at the tail end here, you will just add electrons here in the inversion. Okay, that's the low energy point of the charge stored in the capacitor, because that maximizes the capacitance in the system. So we're really only looking at differential electrons that are minority carriers in the semiconductor. Okay. All right. So that means roughly we are just again piling up charges like an accumulation close to the interface. Okay. And again, it's not exactly at the interface because the semiconductor has band bending, just like with in the accumulation case. So we will introduce this series capacitance again. Okay, so we'll introduce this series capacitance again, and we will have an inversion capacitance that is has an effective inversion width that we distribute our electrons over. Okay, so that is why in an ideal sense it jumps back up to ideally to 1, where you take the capacitance to be just the oxide capacitance. Obviously, it is a series capacitance. It doesn't quite hit 1, but it's close to 1, right? But nevertheless, W inversion is is finite, so the capacitance is there. Okay. Now, keep in mind again that the time it takes to generate carriers through traps is of the order of milliseconds to microseconds. Okay, so if you're operating the system in times faster than that, if you're operating faster than megahertz for the microsecond piece, then you cannot generate all these electrons here fast enough. Okay, so that means after you have reached a steady state, what we assume, but then we keep wiggling the AC signal, there will be electron charge here. There will be inversion charge. There is a channel of charge, but you will not add or subtract charges fast enough to follow in that inversion layer, but you will have to do that here at the depletion area. And if that's the case, we're going back to the mode where we have a depletion behavior in the semiconductor. Okay, so that's where we're going now in the low frequency response. Here we're just going into this branch again if we're following in low frequency. All right. Now, as I mentioned, there is a finite inversion width. So there is a series capacitance that has a finite value. Okay. So in reality, this curve can't quite go to the same original value it had in the in this case here. Okay, where we're in accumulation. All right. So it will not climb up fully here, even in a low frequency response. And that has to do with the charge is being distributed in the semiconductor not exactly at the interface, but a spatial distribution. So you have charge at the interface in an ideal way here. So you have a delta function here of positive charge, and you will have sort of a pile of charge of electrons here, and you will have depletion charge here on this side. And this charge has a moment, spatial moment, and it's not exactly at zero. So there is a separation of, say, a delta function representation of the total charge. If you calculated this first moment of that distribution, you will find it's not at zero. It has a certain width. All right? Therefore, it can't climb up that really far enough. That means for the capacitive response of the system, you can think of this as having made your oxide a little bit thicker. Electrically speaking, you made your oxide a little bit thicker. All right. So let's calculate. Well, here's just a statement that with this inversion charge, the overall capacitance will be smaller than the pure oxide capacitance. Okay? Now, you can still write down these expressions like what we had done before. And what you can do is you can begin to lump these two capacitances together in some equivalent oxide thickness. All right? And you can calculate that equivalent oxide thickness as being consistent of the oxide thickness and the electrical width of that distribution of electron charge in inversion. Okay? And that term is larger than the oxide itself. So when you go to a conference, talk to experimentalists or to theorists that are designing transistors, they talk about an EOT, which is the equivalent or the electrical oxide thickness. That is what they mean, and that really describes, in a sense, also the width of the electronic channel in which you do have charges distributed. Also, if you have a system like this, as I mentioned, if you have a quantum mechanical charge distribution here, so I'm sketching the band edge diagram in a rudimentary way. This charge up here is going to have wave functions like this that clearly separate the charge from the oxide. Now, if you make a smaller and smaller device, these quantum effects become stronger and stronger. So you will separate the charge more and more away from the interface. So this equivalent oxide thickness plays a more important role in small-scale devices. So EOT is actually quite important in super-scale devices at the nano region that we have today. Okay. Now, let's look at the high-frequency response at inversion. As I mentioned before, you really can only add and subtract charges here at the tail end of the depletion region. And again, you can argue that you have an oxide capacitance like this. This didn't change. But now we're separating the additional differential charges in the semiconductor further away from the oxide junction of the semiconductor. Okay, so what happens here? Again, we have very fast response for the majority holes like this. But if we are, again, if we are in inversion here, these carriers up here just can't follow as fast, and we have this high frequency response. So we do have, as I said, we have charge sitting here, but it cannot follow the AC signal. So the only thing that can follow the AC signal is out here at the tail end of the depletion region. All right, that's how we have this high frequency response. Now, let's look at what we just derived, where we said basically an accumulation, your capacitance is flat. Obviously, it's not exactly flat because even the holes have band bending as they accumulate against the interface. Even the majority carrier holds, so it's not a perfectly flat capacitance. So there's bending here. And we also talked about an EOT, which is really band bending as well in the semiconductor, in the depletion and inversion region. So you're not perfectly square here either. And in your ideal model, you can read off two critical parameters. The blue dot really indicates this flat band voltage we started to define from, where you have flat Fermi levels, flat bands. This is the shifted curve to this particular point where all the bands are flat. And in red, we see the red dot here represents the threshold voltage at which the inversion carriers are starting to pile up when they start to build. And you can only, as I said, see that at a low frequency response. At high frequency, the curve just continues down. All right. So that really concludes the small signal response, and then we'll look at the large signal response in the next subsection. See you then.